Welcome to AP Daily for AP Chemistry, topic 3.10, solubility. In this video, we're going to talk about how substances are only soluble in certain solvents, and we're going to describe the intermolecular forces and attractions between those particles. My name is Jordan Rose, and I teach at Free State High School in Lawrence, Kansas. I'm excited to be here with you today. Substances with similar intermolecular attractions will tend to be soluble or miscible in one another. Ionic compounds will tend to dissolve in polar solvents because cations interact with the negative dipoles of water molecules, while anions interact with the positive dipoles. So remember that ionic compounds in a water or aqueous solvent, or a non-aqueous, so not water, polar solvent will dissolve into charged particles. Those charged particles are going to actually interact with the solvent particles, and as we talked about in a previous video, they are going to actually, the solvent particles are going to orient themselves around the different particles of the ionic compound in order to have the strongest intermolecular attractions. Molecular compounds that do not have dipoles and have predominantly London dispersion forces are going to tend to dissolve in nonpolar solvents. The larger and more polarizable the electron cloud, the more interactions are going to occur within the solvent, with the solvent. You may have heard the phrase like dissolves like before. This indicates that nonpolar solutes are going to tend to dissolve in nonpolar solvents, and polar solutes are going to tend to dissolve in polar solvents. The degree of polarity and presence of intermolecular forces determines the solubility in a particular solvent. So remember that when I'm describing like dissolves like on an exam question, I need to make sure that I am explaining it and going through talking about intermolecular forces and attractions instead of just giving a phrase. So if I look at this, for example, I see in this image that water has a very polar structure. So water molecules are all oriented to maximize their interactive forces and attraction forces. And I see here that the hydrogen parts of the water that are partially positive are oriented towards the partially negative oxygen parts of the water. So all of those different water molecules are going to be highly attracted to each other, and that forms a polar solvent. And so if I have two polar things together, remember that that is going to be miscible or dissolve with one another. I noticed in oil that I have just carbons and hydrogens together, so I don't have any polarity of those molecules. It's very symmetrical. I don't see any terminal ends that are different. And so remember that nonpolar with a nonpolar, so those particles with each other are going to also form a solution because like dissolves like. So we see that those intermolecular forces, those London dispersion forces, are all going to be present and attracting each other. However, when I put water with oil, because I have a polar compound in water and I have a non-polar compound in oil, those actually do not mix. They form a suspension. And so I do not have a solution in that case because they don't go together because the particle interactions are so different. Let's look at some examples. So in this case, sodium chloride is we're asked to say sodium chloride is least soluble in which of the following liquids. So if I'm looking at my answer choices, I first want to think about, is sodium chloride, what type of compound is that? So I know sodium chloride is ionic because I have that metal sodium and that halogen chloride there. And so if I have an ionic compound, I know that's going to tend to form those charged particles in solution. And therefore, when I'm solving or when I'm making those charged particles, they're going to be most attracted to other polar solvents where they're going to have charged ends. And so what I'm going to look for at these different answer choices is which one of those are polar and which one of those are non-polar. Because if I want the least soluble, I want the one that is least polar or non-polar. So in choice A, I have water, which we just discussed in a previous slide as being very polar. In choice B, I have carbon tetrachloride. So here I have a tetrahedral geometry, and I know that all of those ends are exactly the same. So I have a very symmetrical molecule. In this case, that would be non-polar. And I look at choice C, I see that I have hydrofluoric acid. And so in that case, I once again have a very electronegative fluorine pulling electrons towards it. So therefore, I've got some polarity in that, and I can form hydrogen bonds in that as well. On D, I see that I have methanol. So in this case, I have that hydroxyl group again that can form hydrogen bonding interactions as well. So I have a very polar molecule in that case. And then at the bottom, I have acetic acid. So once again, I've got this ionizable hydrogen there. I've got this kind of OH group that can actually form some bonding there as well, some interactions, some polar interactions there as well. So therefore, I'm going to say that my best answer choice here would be B, carbon tetrachloride, because that is the one that is non-polar, and sodium chloride would be least soluble in that one. In the second question, of the following organic compounds, which is least soluble in water at 298 Kelvin? So once again, in this case, I want to look, if I'm least soluble in water, I want to look at which one of those is nonpolar, because we know that water is polar. So here for methanol, I see that I have a hydroxyl group on there again. So we just talked about how those alcohols are very polar. So that would be very soluble in water. Here I have propanol again, for B. And so I see that hydroxyl group once again. So both of those alcohols are going to be very soluble in water with those hydrogen bond interactions that are possible. C, I see hexane. So I have a very symmetrical molecule there with a 6-carbon chain. So therefore that one is not going to be soluble in water because it is nonpolar. And then I also notice at the bottom I have glucose and acetic acid again. Both of those are going to have polarity and some induced dipole forces that can actually form attractions. And so therefore we're going to have our best answer choice as C, the most nonpolar molecule. Let's practice together. In this question, use the information in the table below to respond to the statements and questions. And remember that your answer should be in terms of principles of molecular structure and intermolecular forces. So whenever you see that in a prompt where it's kind of directing what your answers should be, make sure that you go back and check after you've answered the question to make sure that you actually gave it in the same language that the prompt is asking you to do it in. So identify a compound from the table that is nonpolar and make sure that you justify your answer. Also, ethanol is completely soluble in water, whereas ethane-thiol has limited solubility in water. Account for the difference in solubilities between the two compounds in terms of intermolecular forces. Stop the video here and try this problem on your own. So my first prompt asked me to identify a compound from the table that is nonpolar and justify my answer. So here I could have chosen I could have had two different possible answer choices. So here when I'm looking at my table, I notice that ethane and ethyne are both very symmetrical molecules. And so either one of those could be identified as nonpolar, because we notice that the ethane or ethyne molecule is all the bond dipoles are going to cancel out. It's very symmetrical. There's no terminal ends that are different. So all of our dipoles would cancel in those molecules. Whereas in ethane-thiol and as well as in ethanol, we have those different ends. We have that kind of SH end and that OH end that is going to create some asymmetry and going to create some dipole forces. Please do notice when I'm answering this question that my explanation must refer to the shape of the molecule. So you can't just give generic statements that say things like all hydrocarbons are nonpolar or the carbons are surrounded by hydrogens. You can't really say something that's just a generic phrase. You have to be very specific and talk about the structures of those molecules as you're answering your question. My second point is trying to explain those differences between ethanol and ethane-thiol. So in this case, when I'm looking at those two, the difference notice is that I have a sulfur in one and I have an oxygen in the other one. So ethanol is able to form those strong hydrogen bond interactions with water, whereas ethane-thiol does not have that similar capability. The formation of those hydrogen bonds is going to increase the attraction between molecules of ethanol and molecules of water, making them more soluble in each other. So even though you've got some dipole-dipole forces going on there in ethane-thiol, it's not going to be as strong of a force as the ethanol hydrogen bond interactions that can form with the water. Please notice that your answer must clearly focus on solute-solvent interactions. So just mentioning hydrogen bonding does not earn the point. So sometimes what happens is that students will say something like, ethanol has hydrogen bonding, and that would just be your final answer. And that would not actually earn this point. So you definitely have to talk about what the different molecules, how their interactions are with water in order to earn this point. You also need to make sure you always talk about both molecules in your answers in order to earn your points. So what should we take away? The overall concepts here that we want to know from this section is that substances with similar intermolecular attractions are going to tend to be miscible or soluble in one another. Substances with dissimilar intermolecular attractions are going to tend to be immiscible or insoluble in one another. So whenever I'm talking about why something dissolves in something else or why particles are attracted to some solvent, you always want to think about intermolecular forces and start describing those in order to earn your full points and to make sure that you are understanding the question and answering the question completely. Thank you for your time today, and please join me in our next video where we're going to be introducing Welcome to AP Daily for AP Chemistry, topic 3.11, Spectroscopy and the Electromagnetic Spectrum. In this video, we will be talking about the relationship between regions of the electromagnetic spectrum and the types of molecular or electronic transitions associated with those regions. My name is Jordan Rose, and I teach at Free State High School in Lawrence, Kansas. I'm excited to be here with you today. Spectroscopy is the study of matter's interactions with electromagnetic radiation. Matter can absorb or emit radiation in different regions of the spectrum, and those regions are associated with molecular motion or electronic transitions. Microwave radiation specifically is associated with transitions in molecular rotational levels. Infrared radiation is associated with transitions in molecular vibrational levels. Vibrational states of bonds require more energy than molecular rotations. Infrared has a higher energy per photon than microwave, therefore a higher frequency and shorter wavelengths than microwave. Ultraviolet or visible radiation is associated, ultraviolet and visible radiation are associated with transitions in electronic energy levels, so electrons being promoted.
Okay, so electromagnetic spectrum, we kind of already talked about, so this should kind of be review. The only thing that maybe you should pick up more on this time, especially for the AP test, that if they ever talk about microwave radiation, those molecules are rotating. Infrared is a vibration, so that's what you want to associate it with. So those molecules in there are vibrating. And then ultraviolet and visible radiation, that's when we talk about those electrons moving up and down from each energy level. So as they move up an energy level, they're absorbing energy. And as they move back down, they emit energy. And so the electromagnetic radiation spectrum, she's going to show it in a little bit, but we kind of have to know roughly where everything is on that spectrum.
Here's an example of the electromagnetic spectrum. And in this, you can see that we have microwaves at a very long wavelength compared to our ultraviolet light. We see that our microwaves have a lower energy and a lower frequency as well. Infrared is kind of in the middle of those two. And when we move over to the visible and ultraviolet, we see at that point we have shorter wavelengths as well as a higher frequency and higher energy as well. Let's look at an example together. The diagram above represents the absorption spectrum for a pure molecular substance. Which of the following correctly indicates the type of transition observed for the substance in each of the regions of the spectrum? And so in this example, we have three different regions, X, Y, and Z, and we see that we are getting absorption data for each one of those. So our multiple choice answers are going to give us some different areas. It's going to look at each of the different regions, and it's going to associate each region with a specific type of motion. So as we just mentioned a second ago, we want to notice that both UV radiation and visible light are going to involve electron promotions. And we also want to make sure that we noticed that we had our microwave wavelengths were going to be our molecular rotations, and the infrared is going to be our molecular vibrations. So if I go through and go look back at my spectrum here, and then I compare that to my answer choices, I notice that region X with the electronic transition matching my ultraviolet and visible. I notice that I have region Y with my molecular vibration, which is going to match my infrared, and my region Z, which is going to match my microwave with the molecular rotation. So my best answer choice here is going to be D. Let's do a practice problem. N2 molecules absorb ultraviolet light, but not visible light. I2 molecules absorb both visible and ultraviolet light. Explain these observations. Go ahead and stop the video here and try this problem on your own. So as we mentioned a minute ago, both types of these are going to involve electron promotions. The UV radiation is going to be more energetic than the visible light. And since the I2 can absorb visible light, there are low-level transitions in I2 that don't exist in the N2. So when we're looking at answering this question, we need to make sure we talk about both N2 and I2. We want to compare and contrast both of those and kind of explain why these observations are happening. So we'll say something about visible light does not produce those transitions between electronic energy levels in the N2 molecule, but does in the I2 molecule. Both the visible and ultraviolet can promote electrons to higher energy levels. Ultraviolet light is more energetic than visible light, so there must be some lower energy electron transitions available in those I2 molecules that aren't present in N2. And we actually know this because we can actually use the visible light as a tool for differentiating I2 from N2. And this is exhibited by the fact that iodine vapor has a deep purple color, whereas nitrogen gas is colorless. So what should we take away from this section? The differences in absorption or emissions of photons in different regions are going to be related to the different types of molecular motions or electronic transitions. Microwave radiation is associated with molecular rotation levels. Infrared radiation is associated with molecular vibrational levels. And ultraviolet or visible radiation is associated with any transitions in electronic energy levels. Thank you for your time. Hi, welcome to AP Daily for AP Chemistry, topic 3.12, the photoelectric effect. This video is going to explain the relationships between wavelength, frequency, and energy that occur when a photon is absorbed or emitted. My name is Jordan Rose, and I teach at Free State High School in Lawrence, Kansas. I'm excited to be here with you today. Spectroscopy is the measurement of spectra produced when matter interacts with or emits electromagnetic radiation. The light that is emitted, absorbed, or scattered can be used to identify and quantify substances. So at the bottom of this image, you can see that we're talking about the absorption or the emission of electrons to their excited or ground states. You can also see that kind of as a generic way of thinking about spectroscopy, that you have your electromagnetic radiation hitting a sample, which is then processed through the spectrometer, and then you get a readout. The wavelength of the photon is related to the frequency of the radiation. And we use the formula C equals lambda nu, where C is equal to the speed of light, either given as 3 times 10 to the 8th meters per second, or 3 times 10 to the 17th nanometers per second. Lambda is a symbol we use for wavelength, and that can be given as in meters or nanometers. So it's important to pay attention to the units and make sure you're matching your constant. And then nu is equal to the frequency, which is given in the unit of hertz, which is the same as 1 over seconds. When a photon is absorbed or emitted by an atom or molecule, energy is increased or decreased by an amount equal to the energy of that photon. The energy of a photon is related to the frequency of the wave through Planck's equation. So we use the formula energy equals Planck's constant times frequency, or E equals h nu, where E is energy of the photon in joules, h is Planck's constant, 6.626 times 10 to the negative 34th joules seconds, and nu is equal to frequency, which once again is hertz or 1 over seconds, the same unit. Let's look at an example together. So here we have a complete photoelectron spectrum of an element in its ground state. Calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom of this element. And there's a hint added on here that the valence shell has the least binding energy. So remember that binding energy is talking about how easily an electron can be removed or how attracted it might be to the nucleus. So the valence shell is going to have the least binding energy. They're going to be less bound to the nucleus. There's kind of a greater distance from that valence shell to the nucleus, and they're going to have a less attraction to the nucleus. There's a less effective nuclear charge. So here we see that the one that has the least binding energy is going to be 0.98 times 10 to the negative 18th joules.
Okay, so if you remember from the beginning of this unit, you were given these spectrums, PES spectrums, and you had to assign like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that type of thing. And we knew that if we're over here on the left-hand side, we are closer to the nucleus, our electrons. And if we move all the way to the right, those are our valence electrons or outermost electrons. So now these energies, we can use them in those problems using those equations to calculate energy. We can calculate wavelength, frequency, that type of thing.
So if we want to calculate wavelength in meters of this radiation needed to remove an electron, we first are going to need to rearrange some of our equations. So since we know that energy is equal to Planck's constant times frequency, and we know that the speed of light is equal to wavelength times frequency, we can rearrange and solve our equation for frequency and plug that back into our energy equation.
So if you do not want to rearrange an equation like that, the first thing you can do is you can use this second equation here, solve for frequency, and then you can plug that into, well, actually, they want you to calculate the wavelength. So what you can do is you can solve for frequency using the energy equation, and then you plug it into this equation to find wavelengths. You could do it in 2 steps, or you can rearrange the equation, rearrange equation and just use one.
So we can say energy is equal to Planck's constant times speed of light over wavelength. So then I can solve for my wavelength by taking Planck's constant times the speed of light divided by energy, which is what we have from our PES spectrum. So here we can plug in our values and we say wavelength is equal to Planck's constant 6.626 times 10 to the negative 34th joules seconds times our speed of light 3.0 times 10 to the 8th meters per second, and divide that by the binding energy from our PES, so 0.980 times 10 to the negative 18th joules. And when we do this calculation, we will end up with a final answer of 2.03 times 10 to the negative 7th meters for our wavelength. And we do want to double check and look at our prompt, and we see that our wavelength was supposed to be calculated in meters, so that matches our answer.
You'll notice that sig figs, her final answer, she has 3 sig figs. And the reason why she has 3 sig figs is because our energy down here is 3 sig figs. 1, 2, 3. Remember, for constants, these two are both constants. We don't take them in consideration for sig figs.
Let's practice. Here we have a free response excerpt. In the upper atmosphere, ozone molecules decompose as they absorb UV radiation, as shown by the equation below. Ozone serves to block harmful ultraviolet radiation that comes from the sun. And we are given a balanced equation where O3, in the presence of ultraviolet radiation, yields O2, oxygen gas, plus atomic oxygen. A molecule of ozone absorbs a photon with a frequency of 1 times 10 to the 15th hertz. How much energy in joules does the ozone molecule absorb per photon? We're also given some information about the minimum energy needed to break an oxygen-oxygen bond in ozone, which is 387 kilojoules per mole. Does a photon with a frequency of 1 to the 15th hertz have enough energy to break this bond? Support your answer with a calculation. Go ahead and stop the video here and try this problem on your own. So first, let's look at the beginning part of this question. A molecule of ozone absorbs a photon with a frequency of 1 to the 15th hertz. How much energy in joules does the ozone molecule absorb per photon? So we're going to go back to our energy equation. Energy is equal to Planck's constant times frequency. I can plug in Planck's constant, 6.63 times 10 to the negative 34th joules seconds, times my frequency that's given in my prompt of 1 times 10 to the 15th hertz. That gives me 6.63 times 10 to the negative 19th joules per photon. So 1 point is earned for that correct answer. The next part is giving me the minimum energy needed to break an oxygen-oxygen bond in ozone, which is 387 kilojoules per mole. And it asks me, does a photon with a frequency of 1 times 10 to the 15th hertz have enough energy to break this bond? Support your answer with a calculation. So I first earn 1 point for calculating the energy from my frequency that's given. So I know that on the previous part of this problem, I calculated my joules per photon as 6.63 to the negative 19th joules per photon. And I want to convert those photons into moles because I noticed that this question is giving me an answer in energy per mole. So I'm going to multiply by Avogadro's number, 6.022 times 10 to the 23rd photons per mole. And then I also want to make sure I convert joules into kilojoules because that's what my unit is in the prompt. So I'm going to divide by 1,000 as well to end up with a final answer for my energy of 399 kilojoules per mole. The second part of this problem to earn a point is asking me how this compares to the energy needed to break that oxygen-oxygen bond. So the second point is earned for the comparison of those bond energies. So I can earn this point by saying something about how 399 kilojoules per mole is greater than 387 kilojoules per mole, and therefore this bond can be broken. So what should we take away from this section? When a photon is absorbed or emitted by an atom or molecule, the energy of the species is increased or decreased by an amount equal to the energy of the photon. The wavelength of the electromagnetic wave is going to be related to its frequency and the speed of light by the equation c equals lambda nu, or speed of light equals wavelength times frequency. The energy of a photon is related to the frequency of the electromagnetic wave through Planck's equation, E equals h nu, or energy equals Planck's constant times frequency. Thank you for your time today, and please join me in our next video.